It took me like a week or so to figure out, but yeah, it works. Back to you.
Yeah, thank you. Yeah, that was the story. So I first got the transmitter board and implemented that, then got the receiver board, also sent one of the receiver boards back to Turkey to Merlin to work on it. So while I was working on the transmitter, he was working on the receiver side. So we don't need to be all together. And on the receiving part, then I got the receiving part and implemented the latest version, which combines, we just threw out this LCD display bit because we don't need it. So the transmitter, the receiver, and the receiver display, which is the common display for receiver and transmitter, was the final design for us. Of course, you can build it separately if you want to use only transmitter, only receiver with this, or use totally different transmitter and receiver. It's up to you. I think we will not change that approach in our next design. So let's have a quick schematic story. We know what's inside, so you can imagine how we connected the lines, etc. But let's have a schematic look and how it works. The ADF 4360 was the one of our local oscillators. We copied everything from the data sheets, or the evaluation boards. As Barb mentioned, we took photos of the evaluation boards, zoomed in. If they don't have, let's say, the gabbers or the pictures in their data sheet, we copied what has done. Also, we exactly the same tube was being used in the Address Research USRP2 modules, daughter boards. So we also zoomed into those and to see what the lengths of the lines should be, what capacitor they use, what are the distances, what are the orientations for place the components in the same place. Because yes, I have a high frequency experience, but not that much. So copying was the first step to learn something, and we did that. So it's easy. Not too many external components, those are all for power supply, and it's just a filter, and you can program it from a SPI that you can get any frequency you want. There were some libraries from analog devices that we were not able to use properly. I found some projects on GitHub, so I had to combine all those together to have a proper Raspberry Pi Pico working version. On the IQ demodulator side, we have the AD8348. The more complex part is this loop filters, and of course we copied some. But the data sheets has a lot of information about how to design this, and they have a software to design this loop filters easily. So what it does, it gets the radio frequency in and it gives you the IQ data out easily in a positive and a negative. So it's the I positive, I negative, Q positive and Q negative. And of course, you need to do some, when generating the I and Q, you need to do some balancing of DC inputs to have the I and Q in place. So in the first prototype, you will see that we have some variable resistors just to manually do that work for us, and it worked and we got the values. Now in the next version, we will use the values we found in this trial. What else I can say? Nothing, so it's a good demodulator. And of course, we discussed that, do we need an LNA filter or something in the, because the LNB output is only 60 dBm, then we have 45 dB gain, and it's more than enough we need. Do we need to put, yes, no, we discussed that a lot, and we found that LNA on JLC PCB, which was very cheap. We said, okay, let's put it there, then we can just put it short and we don't use it. Let's try it. With this LNA, I went below minus 120 dBm, but the minimum I can reach was the 120 dBm, and this device was still receiving it like 5.9 plus. So it was more than we need. So we thought that yeah, someone can use this for VHF or UHF devices. So the LNA is doing good job here. Also, we found another cheap filter online. So we used that. Yeah, that one. So just to filter out the frequencies that we don't need on the output of the LNB, just to filter those out. A cheap solution, of course, you can use a better filter after your LNB, but this is more than enough, I can say. Or you can just short circuit both and use the output. Of course, to the 83, 40, 48, I just put it.
46.
Yeah, 8340. Yeah, 8348 has 70 megahertz bandwidth. So before applying this to the MCU ADC, we need to filter it down to a few hundred kilohertz or more. So we have a op-amp filter here just to minimize the output. So we have the, let's say, 1 kilohertz bandwidth of I and Q data that we can directly feed into our MCU and convert to digital. Of course, some analog parts. For this device to have a speaker or a headphone, we put amplifiers on the device because it will be a portable device. Whatever headset you have, you can plug it in and you can start working with the device. So this is the analog amplification part. So the TX part, same local oscillator, same circuit, just the component values are different to generate a different frequency because, yeah, that's all I can say. Yeah, this is stability. Maybe you will ask it at the end, but what is the stability of the device? The frequency stability. It's all based on this tiny TCXO or crystal you use here. We just use what GLC PCB has, and it did great job. I think it was 0.1 euro
Yeah.
something or something.
And it was like, I think, 1 ppm or something like that.
Yeah, it was not too good. It was cheap, so we just used it to see. We said, okay, the frequency can drift, we can have some drift, but we know the reason. We can blame this guy, but it didn't happen. So we kept that one. If you want more stability, here you can use a GPSDO or something else just to feed 10 megahertz into the system, or a more stable TCXO might do for you. So it's stable, as we define. Yep. On the modulator side, we just put the INQ data after the filters. I need to reverse this, yeah. First this one. Yeah. Normally we have the PWM outputs on the TXI and TXQ. It's a PWM signal, not a sine, not a square wave. It's a PWM going back and forth all the time, depending on the I and Q value. Then we have this simple filter here, the low pass filter, to get a kind of sine out of that, which is, let's say, 0 degrees. Then we just do a conversion to get the positive and the negative values of those. Here we don't have any gain, so it's just a buffer to invert the signal. So we have the positive I and negative I, then positive Q and negative Q. So we can feed the AD8346 easily with the positive, negative, and positive, negative. When you apply the local oscillator to here, then you have the RF signal. And you can, even without this one, it's roughly -5, -6 dBm. You can listen it in the next room, or maybe your neighbors can hear it as well. But we put an amplifier on board to drive most of the amplifiers in the market. Just this,
10 milliwatts.
this just amplifies up to 10 milliwatts. So you can that board, the transmitter board, outputs 10 dBm. So you can drive any amplifier you want if you want to. If you don't, the bottom board has this sky part. It's already, amplifier. You put 0 dBm input and you get 30 dBm output. So you can use that output to feed that into an adder, where you can easily find it in the market, and you can get roughly 2-3 watts of power output. Maybe you will talk about the amplifier. Yeah.
So what we did was, first Boris came up to design our amplifier. It scared me because the 4 gigahertz amplifier designing is not my forte. So I suggested something else. What we did was, I designed a carrier board. This carrier board has a power supply to power all the rigs. And here we have the Sky 65135, right? So that's Sky 65135. This goes from, as Boris said, 0 dB to 1 watts or so. And then we have the EDUP. This is a classic Chinese, everyone knows, I guess, when you're 100, 4 to 8 watts. So we just plug it underneath, and everything is built on top of it as stacks. So it becomes a very compact unit.
Thank you. Thank you. Yeah, so this done. Yeah, of course, on the transmitter side, you can use, you may want to use a microphone, just like what we did was we used a 3D printed microphone and a capsule in it. So we wanted to be able to drive a capsule microphone that is plugged into this. And also we had a line, we wanted to have a line in just to plug into computer for the digital modes or other possibilities. So that's the analog part. What does it look like? It looks like something like this. Thanks to Jem, who designed all this part, and it's fully aluminum. We have 2 versions. We said, let's make a chip. So it was a laser cut from aluminum for the front panel. Make it fancy. So it was a CNC milled aluminum block, which looks much more better to me. That's my version. So the outside is like this, and the back side is the amplifier's cooler. And when you get the top out, you see the display. It's a little bit dim here, I guess, but you have the LCD screen underneath and the keyboards, which is the control board. This control board is connected to both receiver and transmitter. So you can use this control board plus a receiver board, or this control board plus a transmitter board, or this control board, a receiver and transmitter board stacked on top of each other. So it controls everything. Normally, the left side is the receiving controls, and the right side is the transmitting controls. But when you do something on the transmitting side, the transmitting MCU informs the receiving MCU, which controls the display, hey, please type this to the screen, please do this, please do that. Hey, you're not there, so I need to draw the screen, and it starts drawing the screen instead of telling what's going on to the receiving MCU. Under that, we have the receiver board. Mostly it's the Raspberry Pi Pico, the IQ modulator, and the audio parts, the op-amps on it. Under that, we have the transmitter board, and the transmitter board has the preamplifier, so it outputs 10 dBm that you can use with your own amplifier, or if you want to use an amplifier, it's on the bottom board that you can use. You can, yeah, this is the wheel. So you plug in 12 volts, that's the power we need. Why 20 volts? Why 12 volts? Because the LMB needs 12 volts. Yeah, we didn't want to do a booster to boost from, let's say, 5 volts to some